So let us little recap on what we did on last day's class. So we were starting with module number 5, which happens to be something like this. All right. So I told you the diversity techniques is what is our main topic of interest is, and that comes in with the fact that we have already established that with respect to BER, how the BER changes with respect to SNR conditions. And to establish the fact of diversity, we need to establish first that how the wireless scenario gives us a very poor BER performance and how we can overcome the problem. Okay, so that is the main objective behind this particular module. And as I said, we will try to focus on the MRC, the maximal ratio combining what is called the equal gain combiner or EGC, the diversity order, what exactly is diversity order, what is diversity as such in general, what is antenna diversity and all other stuff. So these are all we are going to discuss. But prior to doing that, we need to establish the PER expressions for wired and wireless scenarios. That's the first thing. Okay. So keeping that in mind, if you remember on last day's class, I had given you one. First, we started with the performance of a wire line scenario in which we had established that given a transmitted symbol X and given an AWG noise of N, we can find out that Y or the received signal is nothing but the combination of the transmitted signal and the noise part. Now this noise is ideally an AWG noise. We are not considering any multipath that might be happening over here because this is a wired connection. Wired connection means there is a end to end, there is only single line or a connection dedicated line which is present. Hence, there is no such multipath which is existing over here. So that's why X remains as a pure received signal, but it gets affected by the AWGN noise N, which is nothing but the problem with maybe an optical cable or our hardware issues or whatever the noise incorporated with all those stuff. So that can be given also by some form of power density function which is given here, which we don't need, to be honest, we don't need. It is just an illustration because we will need that or we will need this type of an expression later. Okay, I told you that this is the way it is expressed usually. Okay, now in that way, when we went on discussing with BPSK system where we are only considering one bit at a time, we first tried to figure out that what exactly is meant by bit error rate. And we found out that bit error rate is nothing but, in colloquial language, when you are sending 1 and you are receiving 0, or you are sending 0 and you are receiving 1. That's simple as that. So keeping that in mind, we have just discussed about all this, keeping in mind that bit error occurs when Y equal to 0, which means you have received something where the outcome is greater than equal to 0, but you have transmitted X equals to 1, for which you had already seen that we had set it up as minus square root P. So you're supposed to get a negative value, but you have got a positive value in this. So that's why we will consider that this is where the error has happened or a bit error has happened. So keeping that in mind, we found out that what is the condition for BER, because this condition for BER will change a little bit when we go for wireless scenario as well. Now, if you observe here, the main condition was that the noise factor, the N factor, should be if it is greater than or equal to the square root of the power of the signal or the transmitted signal, then we will then we can conclude that definitely there is some amount of BER that is going to happen, even if it is a wired scenario. Ideally, wired scenario will not have any noise. That is what the main advantage is. But even in that, this N we cannot eliminate completely. There will be some noise that will come in. Alright? But if that noise is greater than square root P, then only BER will happen. Noise can be there. If the noise is less than square root P, we don't have any problem. But if it goes beyond square root P, then that becomes a problem. And that is where we calculated what is the probability of error. Again, after some derivation, which we don't need as such, we came up with a solution, which I told you to make a note, is the equation which happens to be the basic equation of probability of bit error with respect to the signal to noise ratio of a system. Now we have observed that the probability of error or PE is given by a function Q function, which again I told you Q function was there already in the first module when we were doing the practical link budget analysis. So the Q function, square root of SNR, this is happens to be the crux of it. All the other discussion leading to today's discussion as well, you will find that we will take the help of this expression alone. So please make a note of this only. So given this, we have solved some question also. Very simple question where we are given an SNR. We will convert that to linear scale. We will substitute in that and we will find out that what will be the necessary bit error rate, and we found out that it is around 7.82 into 10 to the power minus 4, which is very, very minimal, almost equal to 0. Okay. And I have also told you one very important thing, which I think will be useful for your exam purpose as well, is that given that you don't carry any Q table, because Q function you cannot calculate just like that, you need a Q table for it. And there is also certain restrictions of it, of usage and all. The generic expression, the generic way of approximate Q function expression can be given by this factor, which is Qx less than equal to half of the power minus x square by 2, where x is nothing but, in our case, is square root SNR. Alright. So keeping that in mind, we have also solved the same question using the approximate solution, and we found out that it came around 3.91 instead of 7 point something, which is the exact value. But the order will be almost the same. You can see 10 to the power minus 4. So it is very, very small. So first we had established this, keeping in mind that for BER analysis for wired scenario, we are getting a very minimalistic bit error rate. Now we went on in discussing this also. Anyway, I am skipping for the timing because this is QPSK and QAM expression. Now we come to wireless scenario, where, as I said, the discussion is all changing because of the factor small h which comes in over here, where this small h is nothing but, as you can see over here, fading coefficient. It means h is representing the multi-path components or multi-path scenarios that might come in for a wireless case. And that is why the h factor, which was originally, it was all alone. In the previous case, as you can see over here, it was all alone like this, which now has a coefficient along with it, which is small h. And that h, as it is a multi-path component, it is absolutely random in nature. And that led to our discussion of changing the SNR condition as well. So we found out that for fading condition, the SNR fading is nothing but square root of a squared of the A, which is basically the amplitude of the fading coefficient multiplied by the non-fading SNR, which is conventionally like this. So if you have a 10 dB of SNR and you have converted that to linear scale, that should be multiplied by some factor of S square, which is nothing but the amplitude of the path loss component. You can see over here, I have mentioned this will play an important role today also in our discussion. So keeping in mind that this is a important segment. And as you can see, based on this, we had also regrouped the BER performance as well. So the BER, which was Q of square root SNR, is now square root SNR F, where SNR F is indicating the fading SNR condition. And hence, we have substituted S square SNR also over here. Okay. So naturally, we can observe over here that keeping in mind that we have included this S square, and where A is also a random variable, the average bit error rate needs to be calculated, because A square is, or A value is not a constant value. It will go on changing itself. So we cannot take any instantaneous value, neither we can take any peak value. So we have to take an average of it. So that keeping in mind, we have found out the average bit error rate. I told you this is a very, very important expression. Keeping in mind, this is called as a Rayleigh fading distributed average bit error rate. So average bit error rate is given by half of 1 minus square root SNR by 2 SNR. Alright, this is a very important relationship which will be explored even in other studies as well. But for the time being, this becomes our important. So this happens to be my BER equation for wireless scenario, whereas the Q of square root SNR is the wired scenario equation. Alright. So keeping that in mind, we have solved some question and we have found out that for the BER wired, where its value is 7.82, which we have just now discussed again, we are getting around 4.3 into 10 to the power minus 2 for a wireless scenario. Alright, so this is substantially higher compared to wired scenario. I told you that this kind of questions is very common, where we want to give you a comparison between the wired and the wireless scenario in comparison of bit error rate. But if you know the equation, I don't think it will be a major issue if you are calculating it correctly. Okay. So this is where we actually had almost ended our discussion, and we had done another question on this where we found out that based on if you want to keep the bit error rate to be around 10 to the power minus 6, which happens to be a standard value, we are supposed to use almost 43.4 dB, about 43.4 dB of extra SNR or extra power for that matter in order to achieve the same bit error rate. So as I said, as I concluded our discussion on last day as well, that if I want to maintain a SNR, BER which is very low, which we want to have, because bit error rate, if it is very high, it means the loss, it's a lossy condition. We don't want to have a bit error rate. So if we want to keep the bit error rate to be almost equivalent to a wired scenario, so in wireless scenario, we are actually we have to feed in around 43 dB given the conditions are like this. So it's a huge requirement that we have. Okay, we have to boost in lots of powers. This in fact is one of the reason why diversity comes in, which is our discussion for today. All right. So why diversity? We'll find that using diversity, we actually can boost this power to a substantial value without compromising the bit error rate. All right. So this was our conclusion from the first part of it. The next part, which we had done a little bit as well, which we called as the impact of deep fade analysis, which also we had started on last day's class, and this I'll continue from this point onward, is the reason behind this problem with wireless bit error rate. We have established in the previous one that bit error rate is high for wireless scenario. But why is the reason? Why it is happening like this? So one of the reasons, as I told you, that the value of A, which you are looking at as the amplitude or the coefficient of the multipath, that is absolutely random, and after certain calculation we can say that the condition, if you see the amplitude of the multipath, if it is less than 1 by square root SNR, we usually call that that happens to be a deep fading condition. So you can see over here, I've mentioned over here, please make a note of this as well, that suppose you are asked to find out a deep fade. So what is the condition of deep fade? When the deep fade will happen? Okay, so one of the condition is A should be less than, if the amplitude is less than 1 by square root SNR, we usually consider that as a deep fading condition. If it is a deep fading condition, if it happens to be like this, definitely the bit error rate will exist. So based on that, we had found out the probability of PDF. Okay, probability of deep fade. How many times, or what is the probability that deep fade will occur? That is given by 1 minus e to the power minus 1 by SNR. Please make a note of this. This is called as probability of deep fade. This is not probability of error. It is showing that how much is the possibility that a deep fade will happen. So naturally you can understand quite intuitively, the more the deep fade will happen, the more the bit error rate will happen. Simple as that. So that we are going to conclude in the next slide. So PDF, or the probability of deep fade, is given by 1 minus e to the power 1 by minus 1 by SNR. Now you see in the next slide, if I go here and we take the necessary approximation, you observe that that's exactly what I was meant to. That BER, you can see here I have mentioned that BER is proportional to the probability of deep fade. Alright, this can also be discussed and derived also. So you can see over here the process is mentioned, but you don't need that. The only thing that you need is to understand that the bit error rate is directly proportional to the probability of deep fade. So basically the conclusion is, the more the deep fade will happen, deep fade is nothing but high decrease of the amplitude of the signal. If it is substantial, if A is greater than 1 by square root SNR, we don't need to worry. But if the multipath component coefficient goes below 1 by square root SNR, that is where the trouble comes in. And as we don't know that when it will happen, because it's a random scenario, we are calculating the probability of deep fade. And if that probability of deep fade increases, our bit error rate will also increase. So this discussion is indicating about the impact of deep fading on wireless scenario. Why we are having a less bit error rate for a wireless scenario. Now we want to remove that. We now know that it is definitely that the bit error rate will be less in wireless scenario. How to boost it? That's the main objective, and that is where the next part of our discussion comes in, which is called as the diversity technique. Alright. Now this diversity technique can be easily explained by the example that is given over here. I'll try to go one by one so that we can understand this clearly. I'll give you a very small example to understand this scenario. You see this, what is mentioned over here, that there is a transmitter which is present over here and there is a receiver which is present over here at a certain distance, suppose. Now, as we have discussed that in between there is wireless channel. As you can see, these all are wireless channel itself, right? Now, as we have now understood what is deep fade, we are imagining that at certain point, the deep fade has occurred. That means the coefficient of the channel at this point is sufficiently less to that of 1 by square root SNR. Please concentrate on this, okay? If that happens, suppose I have made a cross of it, it means that there is a deep fade that is happening over here. Now, as we have just now established that if there is a probability of high chance of probability of deep fade, naturally my bit error rate is high. The reason is that whenever this value is very high, the connectivity or the wireless scenario, if you imagine the one transmitter to receiver, the connectivity, and there is a deep fade that has happened, so this connection won't exist anymore. This connection won't exist anymore. That is mentioned over here. A is a single link between transmitter and receiver. If somehow it undergoes deep fade of the transmission, that gets lost. Okay, so that is the major concern. Now, if the transmission gets lost, it means suppose transmitter was sending 1, and at that point, due to the randomness of the channel, A has introduced a deep fade. A means the amplitude of the coefficient has gone less than 1 by square root SNR. So this has undergone a deep fade. So means we are sending 1, but the receiver won't receive anything. Or you are sending 0, the receiver won't receive anything. So basically, every time when you are sending something from the transmitter, it is getting wasted. So naturally, there will be bit error rate, high bit error. Understood? So to avoid this scenario, what we have to do is we have to go for diversity. Where the diversity means that instead of a single path between transmitter and receiver, we will consider multiple paths that might take care of the transmitted data from transmitter to the receiver. I'll repeat once again with another diagram. Let me show you this diagram maybe. I'll just zoom it a little bit if that happens to be any good. So you can see what is mentioned over here. So there is one path which exists like this. There is another path which exists like this. There is another path which exists like this. Fourth path is like this. And the fifth path like this. Alright. So there are 5 such paths which is transmitting the same data from the transmitter to the receiver. Now, given that probability of deep fade is high, considering that definitely the deep fade will happen, what will happen? Suppose these are the 2 paths which are getting completely eliminated because of the deep fade. Now, it's very unlikely that all the paths will undergo a deep fade. It might not be the possibility. It can't be. Okay. So, if suppose these 2 paths are also gone, even in that case, you still have 1, 2, 3, these 3 elements which are present with you. Is it not the case? That's basically what diversity is. Suppose you are traveling from Vellore to Chennai through the national highway, right? Now, suppose you have some problem in highway that it is undergoing on some maintenance, some problem is there and you cannot travel. What will you do? You will do bypass. You will go through some other portion of the city maybe and you will reach Chennai airport finally. So that is basically diversity. You find multiple paths which will send the same data over the interval and it will receive at the receiver. And given the fact that we are allowing the deep fade to happen, because sometimes it is impossible to eliminate a deep fade. It is so random. So let the randomness take care of some of this path. Even if that happens, the diversity will make sure that the data which was transmitted from transmitter receives the receiver. That is basically what diversity is all about. So you can see here, it's mentioned that in this case, there are multiple links in between the transmitter and the receiver. and hence it can be compensated. This happens to be the main conclusion that diversity actually improves the system performance significantly. So you can imagine what our target is. We want to make everything wireless in scenario. Scenario wise, it should be wireless. Now, we want to make sure the bit error rate comes down. Also, we want to make sure that the signal which is transmitted, or the symbols which are, or the data, if you say in that way, whatever is transmitted from transmitter to the receiver remains unchanged. Alright, so that is what we are trying to achieve. So in order to achieve that, there are many ways in which diversity can be taken care of. So you can see over here, mostly our discussion will revolve around antenna diversity. I think all of you are pretty much aware of what we call as the CISO communication. So let me just draw that. This is almost everyone would agree that if you have a scenario like this, where we are looking at single input and single output, we call it as a CISO communication. So up till this point, whatever we have discussed, that is basically a CISO communication. Now what we are trying to achieve is something which is given over here. As you can see that for a single transmitter, there are two receivers which are sitting pretty over here. So there is one link L1 and the other one is L2. Can you see the diagram over here? So there is one transmitter and there are two receiving antenna over here. So each of the two receiving antenna will have a path of L1 and L2. Just like I have shown you right now. So even if one goes away, the other will be there. That is how the design should be done. So as you can see, this is where single input is giving to multiple outcomes. So we can call this as a single input, multiple output, or SIMO communication. And as the diversity is attained at the receiver side, because in the diversity, the number of antennas at the receiver side is more, so we call this as a receiver diversity. Okay? Now in the other way around also it's possible that you have two transmitter antenna here and you only have one receiver antenna. Okay? That also is possible. That is what we call as transmitter diversity. And when we combine both, when the transmitter and the receiver diversity are combined together, we call it the multiple input and multiple output, or MIMO technology. So when you are looking at a scenario, you have a transmitter and you have a receiver and you have multiple antennas at the transmitter and you have multiple antennas at the receiver. We call this as multiple input and multiple output. Okay, so I guess all of you at least have heard the term MIMO in your discussion and many times. So that is basically where we look into MIMO OFDM as well, where the back end is OFDM but the process is MIMO. That means there will be multiple input and multiple outcomes which can be possible. Naturally, the more the number of antennas you are including, the more complexity it will become, more complex it will become in terms of the transmission system as well. Calculation wise also it becomes pretty tedious to do it, but ultimately our objective is to attain a goal where we have an increased value of PER or less value of PER, or rather improved performance of a wireless system. That is guaranteed by diversity. There are frequency diversities also, where maybe the frequencies are the signals are transmitted at different frequency slots or frequency pin we call it, and accordingly we can have a frequency diversity also. We can also have time diversity, space diversity also. So these are all different parts of it, even some code diversity also. Many things can happen. But in general diversity, this is the fundamental. Alright, there will be multiple paths which will try to improve the throughput. That's all. Alright. So keeping that in mind, as we take this small example for our understanding, as you can see over here, we have you remember the expression that we had done just a while back, that when we are dealing with wireless scenario, our generic equation was y equals to hx plus n. This equation was there in the previous slide that we have discussed. So same way, now as we have L1, L2 path, L1, L2 path means there will be two set of H1, H2, which happens to be the complex channel coefficients for both these two paths, as is mentioned over here. So this will be my first path, this will be my second path. So this is my first path, L2, L1 here, and L2 is over here. So both of these two paths will have two set of coefficient, and that is given as H1 and H2. Now, as they are H1, H2, naturally we will have two set of equation, Y1 and Y2. We don't need much detail after this. It's just that the understanding of how this equation and these equations are the same. Except that now we have H1 and H2. So you might think that what will happen at the receiver, if I look at it in that way, that I get the value of Y1 and Y2, which happens to be combined with H1 and H2, then what will happen? The reason is that this is where the different algorithmic techniques comes in. There are many techniques like we are trying to discuss MRC today. There will be other techniques like selection diversity. There will be another feedback kind of system that also is there. But those are very old methods. MRC gives you the best result of it. The other solution also I'll show you. Maybe on Monday's class I'll show you. But the thing is, what we're trying to do is, we are trying to give equal weightage to we will sometimes give equal weightage to these outcomes. Or we will sometimes maximally combine them to get the outcome. Simple as that. This you remember one thing. I'll just write it down one. Sometimes we will maximize the outcome. This will be MRC. And when sometimes we will equalize the outcomes, this will be EGC. Just one line if you can't consider in that way. So you get the Y1 and you get the Y2. Now both of these two should be undergoing some algorithmic input. Now how you are going to do that is depending on whether you are doing a maximization of this or an equal combination of it. Maximal ratio combining, equal gain combining. Both the cases it is combining. So you can imagine a scenario that if you have, suppose you have a transmitter, you have a receiver, suppose I have two antennas over here. Okay? The diagram is looking something like this. After this you are getting something like Y1 and Y2. So Y1 and Y2 is here. Now what we are claiming is that this part, the MRC and EGC, how will it work? That there will be some factor. Maybe I'll just write as X over here. Or maybe I'll just put some other word. Z maybe. Let's just put Z1. Maybe a Z1 here. And maybe a Z2 here. After which they will combine and will give you the outcome of it. This is very, very generic although, but this is what the process is. So our role is here and this Z1, Z2 to do some algorithm. That's all. Alright, so we have the transmitter and the receiver and we have L1, L2. We are getting some Y1, Y2. So maybe I'll just write it down again. T is here. This is single outcome. At the receiver, we have two set of antennas. So this is my receiver. Alright. Now at this receiver, we will have Y1 and we will have Y2. Now what I am claiming is that at this point, we will have something as a Z1 maybe. And we might have a Z2 maybe. Which will get combined to generate the final outcome of Y. Now the point is how we are going to find this Z1 and Z2. So when we are combining this Z1 by some process in which we are taking the maximum weightage, we call it the maximal ratio combining. And when we take this Z1 and Z2 by a process where we are giving equal weightage to these weights, Z1 and Z2 is nothing but some weight. It's a weighted factor. So this weighted factor, if by some calculation we give the maximum weightage, we call it the maximal ratio combined. If it is equally given distribution, then we call it the equal gain combined. That's all. That is the generic understanding of it. So many people have gone on finding out ways in Z1 and Z2 can be altered. The weight factor, how it can be altered. But it has been found till date, the maximal ratio combining and in fact EGC at some point, they provide the maximal outcome for the cell. That is why we are discussing about MRC and EGC alone. We are not discussing everything what is there. Because most of them are inferior to MRC. So it's not any point of going ahead with the inferior process for that matter. Alright. But although in the PPT which I'll share with you, In there, you will find some of the techniques, but most probably that won't be needed for your discussion. All right. Now, keeping that in mind, we will try to establish for MRCs for today that what exactly is the value of this Z1 and Z2 is for an MRC. So let me just go ahead with that. So again, no need for all this explanation. This is just for setting up the final expression. You can look at it later. No problem as such. It's not that too difficult. It's just that we are representing this in an array format, in a vector format. That's all. Y1, Y2, H1, H2, N1, N2. So everything, the same thing we are representing in a vector format. That's all. You can see over here that this is represented by a vector format Y bar, H bar, X plus N bar. Does it look familiar? Does it look familiar? Y equal to Hx plus N. So the same way we are trying to establish. That's all, nothing else. So based on that, leave out the calculation part of it. Now, if you observe here, now where the W1 and W2 comes in. Can you see this? This is what I just in the diagram I had mentioned it as Z1 and Z2. In the diagram I mentioned this as Z1 and Z2. These are the weighting factors. Can you see everyone? This W1 and W2 is coming in with Y1 and Y2. Can you see the diagram over there in the board? So Y1 and Y2 was there. Now we are putting some weight on top of it. So that weight factor is W1 and W2. Now how you are defining this W1 and W2 becomes the two different algorithms. That's all. Right? So keeping that in mind with all the calculation done and everything, we come across a scenario where we calculate the SNR. Alright? So you can see the SNR over here is given by, this is considering that we are dealing with a real signal. We are dealing with a real signal. Because remember I told you that for wireless scenario, most of the signals are complex in nature. The channel itself is complex in nature. But suppose the signal is real in nature, the SNR condition is nothing but the weight factor. W is the weight factor, we are calling it in general. So weight factor transpose. H is that impact, the multipath scenario. So H bar, which is a vector form, square multiplied by P, which happens to be the signal power, divided by expected value of W bar transpose N bar. You don't need to do anything. Don't worry. Don't look at it so weirdly. It's just that this is an expression that comes in. Because remember what we are trying to achieve. What we have the expression with PR is equal to Q of square root of SNR. That's the basic equation, right? In the wired we are already established that. So we need to figure out something in terms of SNR so that we can put it in that equation. That is what we are trying to achieve. We had already found out that BER is nothing but Q of square root SNR. Right? This is what the objective is. So for that, I need the value of SNR or the expression of SNR. Given that we have a weighted factor W included now in the calculation. What will happen to that? So that is what being established right now. Okay, so you can see Y, so Y bar or the combined value is nothing but the signal component and the noise component. Everything is same, it's just that the template is followed one by one. Even with the value of this W, the weight factor, it should follow with the same pattern of equation. Okay, it's not that difficult, but anyway, we don't need that much of detail over here. And as you can see over here, we have gone on discussing the finding out both the numerator and denominator. Alright, so here we have done that. And finally, what we are achieving, which I think you should make a note of, is the final expression which comes in somewhere here. Please make a note of this expression. Okay, the rest of the things can be skipped for the time being. SNR expression is given by P by sigma square, which is nothing but SNR again. So this SNR, you can say this is SNR MRC, we can say in that way, SNR MRC is nothing but P by sigma square, norm of H square. This is norm of H bar. H is nothing but the multipath component square, cos square theta. Even this is not that important because in most of the time what we are trying to achieve, we are trying to achieve SNR to be maximum. So you can see the next line over here. Please make a note of this SNR max. This theta also you can ignore. Okay, so theta, it can only happen when theta equal to 0. So our expression becomes something of this nature. Please make a note of this. P by sigma square. So P by sigma square is again, what we can write for P by sigma square? This is nothing but SNR. SNR in normal condition, in wireline scenario. So basically what we are getting is SNR max is nothing but H square multiplied by SNR. Does it look familiar with something? This one? You remember in case of our wireless scenario, we have established something called as S square SNR. We have done that, right? So it's very similar. It's just that instead of A, we are having the channel response here. So that H itself includes A. And while we are taking H, we are taking the amplitude only. So in general, it is the same thing that we are establishing. So this is what we are looking at for the SNR. Now, the final thing that we conclude for today, at least, is the weighting factor. Can you see this expression? So please make a note of this part alone. W bar, which happens to be the vector representation of the weight factor. I told you the weight factor, right? This weight factor is what is actually added up to Y1 and Y2 or the paths. So the factor is nothing but H bar divided by the norm of H. This is called as the MRC weight. So this is called MRC or maximal ratio combining. Why it is maximal? Because we are taking into account the SNR is maximum. That's why it is called maximal ratio combining. What? The combination of weight at SNR maximum. That is why it is called as maximal ratio combining. So for maximal ratio combining, the factor of W is represented by H by or the H vector by the norm of H. The equation is also provided. H bar but square root of H1 square plus H2 square, where H1 square and H2 square the absolute values of the complex values, complex coefficient. Am I okay with this? Please make a note of this because there are a lot of things, other things are there, but just keep a note of this part alone. So if you are trying to find out the weight factor for a maximal ratio combining, you just have to substitute the ratio of the channel coefficient. That's all. In terms of the vector part and in terms of the H bar part. So let me just give you an example and we'll continue from that point. So let me just take an example over here. I think it is already present here. Okay, so this is the question. So let me just show you from here itself. So we have the W which is H bar by H bar. Okay, so this is the maximal ratio combiner as we have mentioned. So ratio of combining weights, I told you right now. So it is a ratio of combining weights as it follows by this equation. Alright. Now let's take a small example of it to understand this clearly. Just see this example. You have L equals to 2. It means there are two parts which we are looking at. The scenario that we have discussed right now. So L equals to 2 and H1 and H2. Please make a note of H1 and H2. As you can see, this is a complex representation that we are looking at. Let me remove this. Alright. So we have 1 by square root 2 plus 1 by square root 2 j. As I said also already in the previous class as well, that H1 and H2 are nothing but the multipath component which are a complex nature. If you remember, I told you that H is ideally represented as A e to the power j phi. Okay. So the amplitude of it, as you can see over here, what we have done, the question is describe the system model using MRC. We'll not go with everything today itself. As you can see here, what we are representing, you can see. H1 is this, H1, H2 is this. So what will be my Y1? Y1 is H1x plus N1. So H1x into N plus N1, H2x plus N2. Now, how do I calculate H1? You can see everything is mentioned over here itself. Why we need that? Because we need to find out what is my maximal ratio combiner, which requires the vector representation of H bar and the absolute, the norm value of H. So basically what we are trying to do is, this is already given in terms of the factor over here. Can you see this? This is in terms of matrix representation. This is basically my H bar. Now what is my H bar norm value? That is calculated over here. So this is calculated, as I said, if we just have written it down right now, it is nothing but square root of absolute value of h1 square plus h2 square. So what is my h1? You know h2, what do you know? You substitute over there. That's what I've done. You can check it on yourself as well, because this is half only. So we can do that calculation pretty easily. So we will get the value of square root 2. So we are getting a square root 2 here, which is substituted over here. Because the formula was h bar divided by norm of h. Norm of h is nothing but square root, which we have calculated here. Alright. Now we do the rearrangement and the multiplication. So the weighting factor, if you say the weighting factor for this is nothing but given over here. So both of these 2 cross 1 matrix we are getting. So this is nothing but the weighting factor. So suppose the question is only asking about what will be the weighting factor for an MRC scenario. You just need to take the 2 ratio of the h. One is the h bar, the other one is the norm of h. And in here, I have given you the process of calculating the norm of h. So, am I clear with this? Now, if you know this, let me not go with the overall expression and calculation. Maybe we can come back later. But at least what we can show you is, if you know this value of W bar, or leave out the W bar for that matter. Suppose I give you a question right now. If you are given an SNR of 10 dB, let me just make a question now. Suppose you are given SNR is 10 dB, right? Find out the SNR MRC. Find out SNR MRC from the set of information that we have received. Can you do that? Given that you have an h and you have estimated what is my h bar as well, estimate what will be my SNR MRC. So question is, find out SNR MRC given SNR dB is 10 using the MRC process. So what was the relationship for that matter? What was SNR MRC? H square, that is norm square. So we get a value of SNR MRC as H square multiplied by SNR. Remember, this SNR value should be in linear scale. Nowhere dB should be used. Even in the wired and wireless comparison, there also I told you, this cannot be 10 dB. It should be converted to linear scale as well. Please convert that. SNR. So SNR is like 10 log of x is equal to 10 dB. So it's basically 10 to the power 1, so it becomes 10. Right? Should I do that? What is the answer you are getting finally? How much? 13 dB. If you are calculating correctly, and hopefully you have done correctly, so you are getting 13 dB. So can you see a small significance over here? The SNR dB, which was in AWGN scenario, a CISO connection in that way. Single input, single outcome. At that point, what was 10 dB? With only 2 branches and with only specific calculation, whatever we have done so far, we are getting a 13 dB out. So the 10 dB has changed to 13 dB. And remember, just a while back when we were discussing about the extra dB requirement for wireless scenario in order to achieve the same bit error rate, I told you that we need more extra dB, extra SNR. So you can see over here, only by diversity order, if you consider path of 2 only, we are achieving a substantial increase in the dB scale of 13. Okay. So naturally, the bit error rate which was supposed to get over here will also have an effect on this as well. We'll see that maybe later. But that is what the conclusion is over here. So what we have learned today is that by diversity, we are trying to achieve a fruitful upliftment of the SNR or the throughput for that matter by multiple paths, which might undergo different fading also. But given the fact that out of the paths, there will be one path at least which will remain as it is. Because the main reason for diversity is that if we can understand the probability of deep fade as probability of deep fade increases, the bit error rate will increase. So we are trying to tackle that deep fading scenario by making sure that there is some alternative path that exists in between. Alright? So keeping that in mind, we have solved this and we have established that SNR MRC is giving you a substantially high value considering the equation that we have done. Okay, so in that way, we can also find out the PER calculation as well. I'm not doing that because it's already mentioned here. So you just have to find out P of SNR. As you can see in this particular example, you are getting an SNR in MRC, which is 4 times that of the power which you are getting. You are not increasing the power, but the MRC technique itself is boosting the power by 4 times. If you have gone through the question, it's nothing but it's just substitution and result. The result is important. The resultant value is you are indicating as, this is at minus 3 dB noise, including a minus 3 dB noise. Okay. SNR is increased by 4P. So initially it was only P, but without doing anything else, we are boosting by 4 times the power. And naturally, if you are increasing the power, where does power comes in signal to noise ratio? Numerator. So we are increasing the numerator for that matter, keeping the denominator to be as it is. So what is the result? SNR is increasing. Because SNR is nothing but P by sigma square. So if P is 4 times, sigma square is as it is, naturally my SNR will be high. And that is basically the requirement what we had, that we need more SNR. So using these techniques, we can boost up the throughput to a substantial amount. Okay? So in Monday's class, when we come back, this is, you can see the generic explanation, we might start it from this point only. So in the Monday's class, we'll try to solve a few more questions, numericals on this, and we'll end up with the EGC as well. Then we'll have a comparison between MRC and EGC. You will find both of them are almost the same, except that the way we are selecting the weight factor is different. That's all. Okay, but performance-wise, almost they are equivalent. We'll see that. All right, thank you.